Hello everyone, today we're going to talk about Dijkstra's algorithm. This algorithm is very well known for finding the shortest path on a weighted directed graph. It has a very widespread application in routing, circuit design, and so on and so forth. So, the overall idea of this algorithm is about finding the optimal shortest path for each node, and we move on node by node until we have considered all the nodes. And then we're going to reach the final solution. The pseudocode is provided on the left-hand side of the slide. We're going to decompose it and explain it step by step with the help of the graph on the right-hand side. So first, we're going to initialize the entire graph by assigning each node to the value of infinity. In this way, we're going to get our work done more easily. First, for the source node, we're going to assign the value of 0 since the distance of the source to itself is 0. And there are two edges branching out from source S, which is to node U and X. Intuitively, we're going to assign them to the value of 10 and 5 since it's the value of themselves to the source. Okay, so to this part we have already analyzed node S, so we have covered. So we're going to paint it black. And then we're going to move on to the smallest uncovered node. So in this case, it's node X with a value of 5, right? Smaller than any other uncovered node. And this part is showed on the line 5 of the pseudocode, extract mean. So for node X, there are 3 edges pointing out to node U, V, and Y. And for node U, this part is more technical because the sum of its predecessor plus the edge weight, 5 plus 3 equals 8, right? 8 is smaller than its originally assigned value of 10. So which value are we going to take? And the final answer is that we're going to take the value of 8. Since at the end of the day, we are finding the shortest path. So we're going to keep the smaller value of 8 and discard the larger one. So the value of U becomes 8. And this technique is called relaxation, as shown on the line 8 of the pseudocode, relax U, V, and W. Okay, and for node V and Y, just same as before, we're going to take the sum of its predecessor plus the incoming edge weight. So node V, it's 5 plus 9 equals 14, and for node Y, it's 5 plus 2 equals 7. And then, same as before, we're going to move on to the smallest uncovered node. In this case, it's node Y. For node Y, there are 2 edges pointing to node S and node V. For the edges pointing to source node, we're going to ignore it since it's not going to make any difference even after we relax it. So for node V, 7 plus 6 equals 13, which is smaller than its original value 14. So same as the previous step, we're going to relax it to 13. Then we're going to move on to U and do the same as before, relax it, and do V, same as before, and relax it. And we're going to do on and on till all the node is covered and painted black. Okay, so at the end, the value of each node represents the shortest path from the source node to itself. So that's all for Dijkstra's algorithm. It's simple, plain and simple, but very effective. And that's all for today. Thank you very much.